Good day, everyone. Today, me, Mr. De La Peña, together with Mr. Ortigueras and Mr. Salcedo, will be presenting our laboratory activity on tsunami prediction using logistic regression. The goal of this study is to predict whether an earthquake could cause a tsunami, based on earthquake characteristics such as magnitude, depth, and location. I'll walk you through what logistic regression is, how we applied it to our dataset, and the insights we gained from the results. Let's begin by understanding the concept of logistic regression. Logistic regression is a type of supervised machine learning algorithm used for binary or multinomial classification problems. In our case, binary classification will be used, predicting 0 for no tsunami and 1 for tsunami. It works by creating a linear combination of input features, for example, magnitude, depth, and distance, and then passing that result through a sigmoid function to produce a probability between 0 and 1. What makes logistic regression robust is that the model adds regularization, L1, L2, or elastic net, to prevent overfitting. This means it avoids relying too heavily on any single feature and ensures that the model generalizes well to new data. So in essence, logistic regression doesn't find relationships in the training data. It builds a probability-based model that stays stable and interpretable. Now let's go to the methodology and analysis. Now, let's go through how we applied logistic regression to our earthquake dataset. Our dataset includes features such as magnitude, CDI, MMI, SIG, NST, DMIN, gap, depth, latitude, longitude, year, and month, and the target variable, tsunami, which is 0 or 1. We followed four main steps. Step 1, we split the dataset into training and testing sets, 80% for training and 20% for testing. Step 2, we applied standard scalar to normalize the features. This step is very important because logistic regression is sensitive to feature scale. Standardizing ensures all variables contribute equally to the model's decision, instead of being dominated by larger numerical ranges like magnitude or depth. Step 3, we train a logistic regression model on the scaled data. Last step, which is step 4, we use grid search CV with cross-validation to find the best hyperparameters, particularly focusing on the elastic net penalty and the saga solver. This automated search helps find the best combination of parameters for accuracy and generalization. These steps allowed us to fine-tune the model before final evaluation.
Now let's move on the model's performance and the insights we gained from our logistic regression results. In classification performance, our model achieved an overall accuracy of 86%, meaning it correctly classified most of the earthquake events. For tsunami prediction, the model reached a precision of 79%, meaning that when it predicts a tsunami, it's correct about 4 out of 5 times. More importantly, it achieved a recall of 91%, which means it successfully identified 91% of all actual tsunami events. This high recall is valuable in real-world context because missing a true tsunami could have a serious consequences. So even if you get a few false alarms, it's much better than missing an actual event. So next we have the ROC curve, which visualizes the model ability to distinguish between tsunami and non-tsunami events. The AUC score is 0.883, which means the model is about 88% effective in differentiating the two classes. The curve rises sharply toward the top left corner, showing strong discrimination and a low false positive rate. So for the feature importance, here based on the model coefficients, the year and magnitude features have the strongest positive influence, suggesting that more recent earthquakes with higher magnitudes are more likely to cause tsunamis. On the other hand, features like NST, number of station, and SIG, the significance score, have negative coefficients, meaning they slightly reduce the probability of a tsunami. To summarize, our logistic regression model is both accurate and reliable, with an AUC of 0.883 and a recall of 91%. It effectively identifies high-risk earthquakes while maintaining interpretability, making it a good choice for practical tsunami prediction systems.
So for our key takeaways, first, we learned that the correct hyperparameter tuning using grid search CV is really important because it helps us avoid convergence errors. A convergence error basically happens when the model can settle on the best solution. It keeps adjusting and never fully stabilizes. By turning parameters properly, we make sure that the model actually converges, meaning it reaches a stable and reliable point during training. Next, our elastic net model gave a great balance between feature selection and generalization. It helped reduce unnecessary variables while keeping the model accurate. Using the standard scalar turned out to be essential. It ensures that all features are on the same scale, so no single feature dominates just because of its numeric range. And finally, for our metrics, We look at accuracy, precision, recall, and one that's new to us, AUC, or area under the curve. AUC tells us how well our model separates classes, not just how many prediction it gets right. So if two models have similar accuracy, the one with the higher AUC is actually better at distinguishing between positive and negative outcomes. That's why understanding AUC really gives us deeper insight into our model's true performance.
Now that we've seen how well the model performed, let's connect the theory of logistic regression to the actual code implementation we use. So first, we have the linear combination. Logistic regression calculates a weighted sum of all input features. In the code, these weights are stored in model, the name of the model, which is model, .cof underscore, and the intercept term in model.intercept underscore. Together, they represent the mathematical formula that model uses to predict tsunami probability. Next is the sigmoid function. It transforms the linear result into a probability between 0 and 1, essentially turning raw numbers into meaningful tsunami likelihoods. In code, we use predict underscore proba to get those probability values for each test sample. Then, we apply regularization. This prevents the model from overfitting by controlling how large the feature weights can become. We use the elastic net approach, which combines both L1 and L2 penalties. And according to our hyperparameter tuning, the best ratio was 0.7. This means our model learns more toward L1 regularization, giving it a better feature selection while still maintaining stability from the L2 part. So next, to train the model, we use also the Saga solver, which is the only one that supports elastic net. We also set max iteration to 5,000 to ensure the model converge properly without throwing any iteration warnings, the convergence errors. And next is feature scaling. Because our dataset includes features with different ranges, like magnitude, latitude, and year, we use standard scaler. To normalize them, and this ensures that all features contribute fairly to the training process. Finally, we use cross-validation through grid search CV to test multiple combination of parameters including C values and L1 ratio. This allowed us automatically identify the best hyperparameters, which gave us the strong model performance we saw earlier. In short, each theoretical concept in logistic regression, from the linear combination to the sigmoid curve, regularization, scaling, and optimization, directly connects to our actual code implementation. This bridge between theory and coding is what makes our model both mathematically sound and technically reliable. And that's all for our group. Thank you.